is area of a trapezoid, so no longer dealing with parallelograms. Okay, when you're dealing with a trapezoid, just like with the parallelograms, you could draw in one diagonal and split this into two triangles. Okay, and if you treated each individual triangle, you could find the area for the trapezoid is still going to be the sum of these triangles. The only difference is in the parallelogram, the triangles were exactly the same or congruent. In this case, they're two different triangles. So we would have to set it up as base 1, height 1, base 2, height 2, but we can still derive it using the same relationship. I'll normally call my base 1 the smaller of the two bases, base 2 the longer of the two. It doesn't matter which one you label which. But if we wanted to find the area for this first triangle, triangle number 1 here, 1/2 base times height, well, if we found our height by extending this side, taking the perpendicular from that opposite vertex, here is my height, h1. Okay, if I find my height 2 for this second triangle, here's my base of b2. My corresponding height is this perpendicular distance from the opposite vertex. Well, what do I notice about these two heights? They're contained in the same parallel, Monica? Well, eventually you could form this into a parallelogram, but in this case, they're just the exact same, right? So if the heights are the same, we could replace h1 and h2 with just the same common value h. And then if we look at these two terms, they do have common factors. They both have a 1/2 and they both have an h. When you remove a factor of 1/2 h from the first term, you're left with b1. When you remove a 1/2 and an h from the second term, you're left with b2. And so if I rearrange this just slightly, I get my area formula for trapezoid is 1/2 the sum of the bases times the height of the trapezoid. And so here is my area formula for a trapezoid. Okay, let's take a look at an example problem involving trapezoid. Okay, if we begin with our area formula, 1/2 the sum of the bases plus the height of the solid, or of the height of the trapezoid. We don't know our bases yet, but we do know what value. The one value we have, which is the height. So we know the height is going to be 24. And so when we look at this height, if the ratio of AB to BC is 3:2, that means, again, the ratio of parts of 3:2, that means we have a scaling factor of 3/2 or 2/3. Now, is AB going to be longer than BC or shorter? If it's 3:2, AB is going to be longer, right? So which of these factors, 3/2 or 2/3, makes something larger? The 3/2. So if we take our given side of 24, multiply it by 3/2, that'll give us this length AB. 2 goes into 24, 12. 12 times 3 gives us 36. So this whole distance here, which I'll call base 1, is 36. Okay. If that's 36, what we can now do is, again, most figures, you'll draw perpendiculars from any vertex. That allows you to work with right triangles. So we create this rectangle as well, so opposite sides are equal. So that length is 24, this length is 36. And if we have this right triangle with a leg of 24 and a hypotenuse of 30, can we find what the other leg is? Yeah, there's two different ways that you can find it. One is to use common triples, right? Is that what you're thinking? Okay, so one way, the easier way, if you can see it, is common triples. Are there any multiple common factors between 30 and 24? 30 is 6 times 5, 24 is 6 times 4. So we have a 3, 4, 5 common triple with a multiplier of 6. So this whole thing was 18 that means our whole base 2 right here is 18 plus 36. So we get 54.